Okay, let's unpack this. Imagine a digital treasure trove, just holding secrets to health, disease, and maybe even the future of medicine.
Hmm.
Every single day, hospitals across the globe are generating petabytes of this data. I mean, a volume that truly dwarfs national
It's
libraries.
staggering.
We're talking about electronic medical records, or EMRs, sometimes called electronic health records, EHRs. And here's the kicker. Their immense, almost unimaginable potential for artificial intelligence.
Yeah, the potential is huge.
So our mission for this deep dive is to really understand the complex, multi-stage journey this data takes. It starts as, a simple input from a clinician, a click here, a note type there,
Right.
and ultimately ends up powering some revolutionary AI model. But don't let anyone tell you this is a simple export and train process.
I don't know. It's far from simple.
It's a formidable pipeline, absolutely packed with challenges every step of the way. Today, we're going to systematically deconstruct how EMR data is processed, evaluated, and ultimately fed into those neural networks that power modern healthcare AI.
Sounds good.
And believe me, we'll be navigating some serious technical complexities along with those crucial ethical considerations that make healthcare AI so, well, unique.
Absolutely. What's fascinating here is the core paradox. This digital treasure is very real, but it's currently locked in a digital vault.
Right, locked away.
Think about it like trying to put together a truly massive jigsaw puzzle where the pieces are scattered across a vast warehouse and the box top with the picture you're trying to build, it's completely missing.
Wow, that's a great analogy.
It's an incredibly intricate challenge. But if we can truly unlock this data, the potential applications for AI are nothing short of transformative.
Like what specifically?
Well, we're talking about clinical decision support that helps doctors make better, more informed choices, predictive analytics for spotting early signs of disease,
Okay.
personalized medicine tailored to your unique biology, and even streamlining the administrative side of healthcare, making systems more efficient for everyone involved.
So if we're starting this grand data journey, where does it all actually begin?
Uh-huh.
It starts right at the source, inside the EMR system itself. And you might be surprised at how complex it is. Literally, from day one, these systems, whether it's Epic, Cerner, or others,
Yeah.
they were fundamentally designed for operational needs, for the day-to-day work of clinicians, not necessarily for powering sophisticated analytics or cutting-edge AI models.
Exactly. That's the key point.
It's almost like trying to turn a perfectly good hammer into a precision microscope, isn't it?
That's a good way to put it. The anatomy of modern EMR data is really a multimodal tapestry. It's woven from three broad categories of data, each presenting its own set of unique challenges and incredible opportunities for AI development.
Okay, three categories. Let's break those down.
Right. First up, we have structured data. This is arguably the most straightforward for machine learning. Think of it as discrete, clearly defined points entered into predefined fields.
Like drop-down menus or checkboxes.
Exactly. We're talking about diagnosis codes like ICD-10, procedure codes such as CPT, medication orders with specific dosages, structured lab results that come back with numerical values, and vital signs recorded neatly in flow sheets.
Okay.
The benefit here is pretty clear. It's readily accessible, it's organized, and it's relatively easy for machine learning algorithms to process. But here's the limitation.
There's always a catch.
Right. It often lacks that rich clinical nuance, that crucial context, or, more importantly, the why behind clinical decisions. It tells you what happened, but rarely the full story or the physician's reasoning.
So it's like getting a list of bullet points, but none of the paragraphs that explain it.
Precisely. And then there's unstructured data, which is this vast, often overwhelming ocean of free text information.
The notes.
Exactly. This includes the clinician's detailed progress notes, the comprehensive admission and discharge summaries, surgical reports, and the interpretations from pathology and radiology. This narrative data is just incredibly rich with context, subtlety, and the actual reasoning behind medical decisions. It's truly where the human element of medicine lives in the EMR. It's estimated that up to 80% of all health data is unstructured.
80%. Wow.
Yeah, making it a massive, largely untapped resource. I remember one project where we were trying to predict patient deterioration, and the structured vital signs would sometimes be stable.
Okay.
But a quick scan of the nursing notes would reveal phrases like patient restless, family concerned. That free text insight was often the earliest warning.
That makes perfect sense, the human observation.
Exactly. The challenge, of course, is unlocking that value, which requires sophisticated natural language processing, or NLP, techniques.
Got it. NLP. And what about that middle ground? I can imagine there's data that's not fully structured, but not completely freeform either.
You're hitting on semi-structured data. These are documents like scanned PDFs from external facilities, perhaps a fax from another clinic, or some older imaging reports.
Okay, so things that aren't directly in the system's fields.
Right. They might have some internal organization, like clear headings or sections in a report, but they aren't directly machine readable in the way a discrete lab value is. So extracting information from these often requires an initial step of optical character recognition, or OCR.
OCR, to read the image.
Exactly, to convert the image to text before you can even apply NLP. This adds another layer of complexity and, unfortunately, another potential point for errors to creep in.
More complexity. Okay, here's where it gets really interesting, especially for those of you who work in healthcare. To make this concrete, let's dive into one of the biggest players in the EMR world, Epic Systems.
Right, Epic, a major one.
Their data architecture is, well, a masterclass in how operational needs can clash directly with analytical ones. It's a multi-layered environment designed specifically to keep the high-throughput demands of live clinical operations completely separate from the intensive resource-heavy queries needed for reporting and analytics.
Yes. Epic achieves this critical separation through what we can call a triumvirate of distinct but very much related databases.
A triumvirate, okay.
At the absolute heart of the system is Chronicles. This is the live, real-time production database that clinicians interact with directly, every second of every day, through their hyperspace user interface.
So that's the live system.
Exactly. It's built on Epic's proprietary hierarchical database management system, historically MUMPS, now Cacheris. Its architecture is incredibly optimized for lightning-fast transactional processing, meaning quick reads and writes of individual patient data.
Gotcha. Fast in, fast out.
Right. The moment a clinician saves a note or places an order, that data is instantly available in Chronicles. But here's the crucial point. Performing complex, large-scale analytical queries directly against Chronicles is absolutely forbidden in practice.
Forbidden. Why?
It would consume immense system resources and could slow down or even crash the live hospital system, potentially jeopardizing patient care. Imagine 1,000 people suddenly trying to cross-reference every book in a library, while 100 others are trying to check out books simultaneously. It just wouldn't work.
Okay, that makes total sense. You can't slow down patient care. So Chronicles is essentially the high-speed operating system, totally optimized for getting things done quickly in the moment. So where does the analytical side of things come in then?
To enable reporting and analytics without risking the live system, Epic developed Clarity. This is a separate, analytics-focused database.
Clarity.
It's populated nightly via an extract, transform, load, or ETL process from Chronicles. Clarity is built on a standard relational database platform like Oracle or Microsoft SQL Server, making it accessible with standard SQL queries.
So you can use SQL Keller. That's more familiar.
Exactly. But the key trade-off here is latency. Data in Clarity is always at least 1 day behind the live clinical data.
1 day behind.
While this makes it unsuitable for real-time operational reporting, it provides a safe and accessible environment for retrospective analysis. However, it's often described as a puzzle of thousands of tables because of its highly normalized structure.
Thousands of tables. Seriously.
Yes, thousands. You might find information for a single patient visit scattered across dozens of those tables.
Wow. That sounds like a nightmare just to get a basic report. How did people even navigate that?
It can be. And then sitting on top of Clarity, you have Caboodle, which is Epic's Enterprise Data Warehouse, or EDW.
Caboodle. Okay, layer 3.
Right. This takes the process another step further. Data is extracted from Clarity and often other non-Epic sources and goes through another ETL process.
Another one.
Yep. In this step, the highly normalized data from Clarity is remodeled into a dimensional data model, most commonly a star schema. This structure is explicitly optimized for business intelligence and analytics.
Optimized how?
It organizes data into fact tables, which contain quantitative measures, and dimension tables, which contain descriptive contextual attributes. This denormalized structure simplifies and speeds up common analytical queries. Epic's own self-service data exploration tool, Slicer Dicer, actually runs on Caboodle.
Okay, so Caboodle makes querying easier for standard reports.
Yeah.
But if I'm a developer trying to build a cutting-edge AI model for, say, real-time sepsis prediction,
Right, that's the key question.
the immediate stark reality is that the standard Epic data sources, Clarity and Caboodle, are fundamentally not designed for that. Is that the ultimate top-line insight here?
Exactly. For that kind of real-time, instantaneous application, you're looking at data that is, by definition, at least 24 to 48 hours old and has undergone one or two major proprietary
Oh,
transformations.
delayed and potentially altered.
Precisely. So for those predict sepsis in the next hour kinds of models, you absolutely need a different data pathway, one that often relies on streaming data directly from the live system, maybe using something like FHIR, which we can talk about.
Okay.
But for retrospective research, population health studies, or models that don't need sub-daily predictions, Clarity and Caboodle are the designated and quite powerful starting points. The EMR's architecture fundamentally dictates what types of AI applications are even possible.
That makes sense. You mentioned earlier that the data is chopped up into the smallest possible pieces. That wasn't just a colorful description then.
Not at all.
It's a direct consequence of a fundamental database design principle. And it sounds incredibly inefficient for analytics. Why would they design it that way in the first place? What's the hidden benefit?
That's a great question, and it really gets to the heart of the operational versus analytical design clash. What you're referring to is database normalization.
Normalization, okay.
It's a core principle for relational databases like Clarity. Its primary goal is to minimize data redundancy and improve data integrity by dividing larger tables into smaller, well-structured ones.
Minimize redundancy. How?
Well, for an operational transactional system, this is incredibly efficient. For example, a patient's name is stored just once in a patient table. It's not repeated every time that patient has an encounter, a lab result, or a medication order.
Ah, I see. So you don't have the same name typed slightly differently in 100 places.
Exactly. This ensures consistency and makes data entry faster and less prone to errors. It's perfect for ensuring that if a patient changes their last name, you only update it in one place.
So it's efficient for saving data and keeping it consistent.
Correct. However, the analytical consequence of this design is immense complexity. A single, seemingly simple clinical concept like a patient's visit or an admission can have its constituent data scattered across dozens or even hundreds of different tables in the Clarity database.
Hundreds, wow.
To reconstruct a coherent, longitudinal patient record a complete timeline of all diagnoses, medications, labs, and procedures associated with that patient, an analyst has to embark on a really complex data sleuthing mission.
Sleuthing, I like that.
They first need to identify the correct tables for each piece of information, and then painstakingly figure out the precise Joyane logic, linking those tables together using a web of primary and foreign keys. It's like having a puzzle where every piece is labeled, but you have to figure out which labels go together to form the picture.
So this task sounds far from intuitive, and it must be a significant bottleneck, right? Who even does this? Does it require a special kind of person?
It absolutely is a significant human bottleneck in the AI pipeline. The sheer complexity of the Epic data model, for instance, has created a demand for a highly specialized role. The clinical data analyst, or data wrangler.
Data wrangler, love it.
These individuals possess a rare hybrid of deep SQL expertise and intimate knowledge of the EMR's proprietary schema. This isn't a task you can just hand to any developer who knows SQL.
Why not? A SQL, isn't it?
Not quite. An analyst can't simply guess table relationships based on their names. They have to meticulously trace the lineage of a data point from how it appears in the Chronicles-based user interface all the way back to its specific table and column in Clarity. This often involves using Epic-specific tools like the Record Viewer and the Analytics Catalog,
Okay.
which act like a Rosetta Stone for their proprietary data.
So it requires deep system-specific knowledge.
Immense knowledge. I remember one project where a seemingly simple question about patient readmissions turned into a 6-month data sleuthing mission just to accurately link all the necessary records across various tables.
6 months.
That
Just
was
to get the data together.
Just to define the cohort accurately, it really hammers home how specialized this role is. The success of the entire AI pipeline hinges on the accuracy of this initial reconstruction.
Because garbage in, garbage out, basically.
It's precisely. A single incorrect join or a misunderstood table context can introduce subtle but catastrophic errors, producing a flawed data set that will silently invalidate any downstream AI model, no matter how sophisticated it is.
Wow.
The steep learning curve and specialized knowledge required for this represent a significant and often underestimated cost and dependency for any organization looking to leverage its EMR data for advanced analytics. It's often the part of the project that takes the longest and requires the most specialized talent.
Okay. Once you've managed to understand the EMR's internal labyrinth, that intricate puzzle you just described, the next hurdle is extracting that data in a robust and scalable way.
Right.
It's about designing the road for the data to travel, getting it out of the EMR and into an AI-ready environment. This is where we start talking about core data engineering principles that bridge the gap between clinical systems and cutting-edge analytics.
Indeed. The fundamental movement of data from a source system to a target analytical environment is traditionally governed by ETL, or extract, transform, load.
ETL. Heard that one before.
But with the rapid rise of powerful cloud computing, a more flexible alternative, ELT, or extract, load, transform, has become incredibly prominent. And this shift has significant implications for how we approach healthcare AI development.
Okay, ETL versus ELT. Break that down.
Sure, in the traditional ETL paradigm, data is first extracted from the source system, like Epic Clarity. It then moves to a temporary staging area where it's transformed, cleaned, standardized, and remodeled to fit the predefined schema of the target system. Finally, this transformed data is loaded into the destination data warehouse.
Right.
Epic's caboodle, which we just discussed, being populated from Clarity, is a prime example of this model. This approach is quite rigid. The transformation logic is defined upfront by IT or data engineering teams.
So it's planned out in advance.
Exactly. It makes it structured and predictable, but often slow to adapt to new analytical requirements or changes in data structure. If a data scientist needs a new feature, they have to put in a request and, well, wait.
Right. So traditional ETL sounds a bit like a highly organized factory assembly line where everything is planned out in advance. But what about ELT? How does that change the game, especially for AI?
That's a great way to put it. Now, with modern ELT, enabled by the immense scalability and cost-effectiveness of cloud data platforms, the last two steps are fundamentally flipped.
Flipped, how so?
Raw or minimally processed data is extracted from the source and loaded directly into a highly flexible and scalable target environment, such as a data lake or a cloud data lakehouse like Amazon S3, Databricks Delta Lake, or Snowflake.
So you load the raw stuff first.
Exactly. The intensive transformation work is then performed after loading using the powerful distributed compute engines of the cloud platform itself.
Ah, transform in the destination.
Right. This shift from ETL to ELT fundamentally democratizes the process for healthcare AI development. In a traditional ETL world, if a data scientist needs a new feature or a different data aggregation, they'd have to file a change request with the data engineering team.
Which takes time.
Exactly. Significant delays stifles the iterative nature of research. The ELT model empowers data scientists to perform their own transformations directly on the raw data in the data lakehouse. Using tools like dbt, Data Build Tool, or Spark SQL,
DBT, yeah.
they can independently create and iterate on multiple, customized, gold standard analytical tables from the same raw source, each tailored to a specific AI model or research question. This fosters the rapid experimentation and agility that are the lifeblood of modern AI development.
So it's faster, more flexible for the data scientists?
Exactly. Moving data transformation from a slow, centralized bottleneck to a fast, decentralized, and highly agile capability.
That makes perfect sense.
Yeah.
So we've established the what and the why of getting data out.
Yeah.
Let's talk about the how. What are the actual components and technologies that come together to build this road you mentioned earlier, this modern data pipeline?
Absolutely. At the very beginning, we have data ingestion. This is about getting the data out of the EMR's analytical database and into your cloud environment.
Okay, the first step.
For batch or microbatch processes, specialized tools like Fivetran can connect directly to the source database. For example, the Oracle or SQL Server instance running Epic Clarity and use techniques like Change Data Capture or CDC. Change Data Capture. It efficiently replicates only new or updated records to the cloud target. This is much more efficient than copying everything every time.
Got it. Only copy the changes.
Right. Next, we arrive at the centerpiece of modern data architecture: data lakehouse platforms. These are hybrid platforms that elegantly combine the low-cost, flexible storage of a data lake, which can handle raw, unstructured data.
Like those notes we talked about.
Exactly. With the robust data management and transactional features typically found in a data warehouse.
Best of both worlds, kind of?
Sort of, yeah. For instance, Databricks is built around Apache Spark and provides a unified platform for data engineering, data science, and machine learning. Its Delta Lake storage layer adds reliability, AC transactions, and performance to data lakes that live on cloud storage. And tools like MLflow help manage the machine learning lifecycle.
Okay, Databricks. What else?
Amazon Web Services, or AWS, offers a comprehensive suite of services that integrate seamlessly. This includes Amazon EMR for managed big data frameworks like Apache Spark, Amazon S3 for massively scalable object storage, which acts as your data lake, and Amazon SageMaker for building, training, and deploying machine learning models at scale.
AWS, right? The big cloud provider.
And then there's Snowflake, a cloud-native data platform that ingeniously separates storage and compute, allowing for immense scalability and elasticity. Healthcare organizations are increasingly using Snowflake to ingest data from both Clarity and Caboodle, then remodeling it into custom schemas optimized for specific machine learning use cases.
Interesting. So they might pull from both Clarity and Caboodle into Snowflake.
Yes, and they often integrate it with non-clinical enterprise data like financial data from Workday to create a more holistic view of operations and patient outcomes.
So we've got the data flowing into these powerful cloud environments. But how do you manage all these complex steps, ensuring everything runs smoothly and on time? It sounds like a lot of moving parts.
You're touching on orchestration, which is essential for managing these complex data workflows. These pipelines can involve dozens of sequential and parallel steps,
Right.
from data extraction to transformation to model training. Apache Airflow has become the industry standard here.
Airflow.
It allows developers to define workflows as code in Python, creating what are called directed acyclic graphs, or DAGs, of tasks.
DAGs, like a recipe.
Exactly like a recipe, where each ingredient or task has to be prepared in a specific order, and some can be done at the same time. Airflow handles the scheduling, monitoring, and retrying of these complex pipelines that might, for example, extract data from an EMR, run a Spark transformation job, and then trigger a model training process.
So it manages the whole sequence.
Right, and managed services like Amazon MWAA, managed workflows for Apache Airflow, simplify the deployment and management of Airflow, allowing teams to focus on building the pipeline logic rather than managing the infrastructure.
That makes perfect sense. So we've been talking about bulk data extraction, getting large historical data sets. But what if you don't need all the historical data, or maybe you need it right now? This raises an important question about real-time data needs in a standard called FHIR.
That's a great point, and it highlights a crucial evolution in healthcare data. An important alternative, and often a complement, to bulk data extraction from back-end databases is the use of modern interoperability standards. Chief among them, HL7 FHIR.
FHIR. Heard a lot about that one. Stands for.
Fast Healthcare Interoperability Resources.
Right.
Unlike the bash-oriented ETL process we just discussed, FHIR defines a standard set of data formats called resources, such as patient, observation, or medication request, and a RESTful API for exchanging them in near real time.
Okay, so it's like a standard language for asking for specific data points.
Exactly. It means an authorized application can make a specific request, for example, get the latest lab results for patient X, and receive a standardized, structured response directly from the EMR. It's like asking a specific question and getting an immediate, direct answer, rather than downloading the entire library to find one book.
That sounds much simpler for developers.
It often is. The challenge, though, is that each EMR vendor might implement the FHIR standard with its own unique quirks, even if it's supposed to be a standard.
The classic standard with variations problem.
Precisely. This is where intermediary platforms, sometimes called interoperability as a service providers, like Redox, provide significant value.
Redox, okay.
They offer a single, consistent API endpoint for developers. A developer sends a standard FHIR request to Redox, and Redox's platform handles the complex task of translating that request into the specific proprietary language or API format required by the target EMR system, like Epic. It then translates the EMR's response back into standard FHIR for the developer.
So it's like a universal translator for healthcare data requests.
Essentially, yes. Dramatically simplifying integration.
And can this go both ways? Can an AI system send data back into the EMR using FHIR?
Absolutely, and that's where it gets really powerful. This pipeline isn't always one way. The same FHIR infrastructure can be used to write data back into the EMR.
Like what?
For instance, an AI model running in a Databricks environment could analyze streaming data and detect an elevated risk of sepsis in a patient. This insight can then be packaged as a FHIR observation or risk assessment resource and sent via a platform like Redox back to the EMR,
Okay.
where it can trigger a real-time alert for the attending physician directly within their workflow. Imagine the impact of AI not just predicting, but also immediately informing frontline care.
Wow, closing the loop, that's huge.
It really is.
Yeah.
This emergence of FHIR APIs creates a competing paradigm to traditional bulk data extraction, presenting a critical strategic choice for AI development teams.
Oh, FHIR for speed, bulk for depth.
That's a good summary. The FHIR API approach is far simpler for developers and ideal for applications that require real-time or near real-time data for a limited set of data points. However, what a vendor chooses to expose through its FHIR endpoints may not represent the complete, granular, historical data available in the back-end databases like Clarity.
Right. They control what you can ask for.
Exactly. For deep retrospective research that requires a patient's entire history, or for models that need access to obscure data elements not available via the API, the complex but comprehensive bulk extraction from Clarity and Caboodle remains indispensable.
So you probably need both.
The future of healthcare data pipelines is likely a hybrid one, yeah, where organizations leverage the speed and simplicity of FHIR for operational and event-driven AI while continuing to rely on robust ELT pipelines for large-scale research and population-level analytics. You essentially need both approaches for different problems.
Okay, so you've extracted the data, you've got it into your cloud environment, whether it's via bulk, ELT, or those slick FHIR APIs. Mission accomplished?
Not quite. Not even close, really.
Not quite. Now, the real work of forging order from chaos truly begins, turning that raw data into something genuinely usable. Even after extraction, EMR data is notoriously messy, incomplete, and inconsistent. It needs significant refinement. In fact, I've heard that this cleaning process can often take up more than half the time of an entire AI project. Is that true in your experience?
You're absolutely right. Data quality is consistently cited as the primary barrier to its secondary use for research and AI. That 50–70% figure for data cleaning and preparation is not an exaggeration at all.
Wow, 70%.
The process of cleaning and pre-processing this data is a meticulous, time-consuming, and utterly critical stage that directly impacts the validity and reliability of any subsequent analysis or AI model.
So what are the big cleaning challenges?
Well, one of the most pervasive challenges is handling missing values. This happens due to irregular patient visits, variations in documentation practices across different clinicians or departments, or simply data not being collected for certain fields.
Well, there's gaps in the record.
Exactly. There are several strategies, each with trade-offs. The simplest, deletion, means removing rows or columns with missing values. But this often leads to significant information loss and can introduce bias if missingness isn't random.
Yeah, you don't want to throw away too much data.
Right. Then there's simple imputation, which replaces missing numerical values with a mean, median, or mode. For time series data, you might use a forward fill or backward fill method, using the last or next observed value.
Okay, filling in the blanks with averages or neighbors.
Sort of. More advanced imputation methods leverage relationships within the data. For example, regression imputation uses a model to predict the missing value, while k-nearest neighbors, KNN, find similar records to infer missing data. For complex temporal data, deep learning models like autoencoders can even reconstruct missing values by learning patterns.
Using AI to fix the data for AI. Interesting.
It can be very effective.
I imagine cleaning this data must feel like a never-ending battle. Do you have any memorable data cleaning nightmare stories that highlight just how messy it can get?
Oh, absolutely. Where to start? I once saw a lab result where the units field was a free text string, and clinicians had entered everything from mg/dl to milligrams per deciliter to m1g for dl to just bloody confusing.
Suckles. Bloody confusing. That's helpful.
Right. Standardizing that was a project in itself. Then you have handling outliers. These are data points that significantly deviate from others. They could be simple data entry errors, like a typo in a lab value, a blood pressure of 1600 instead of 160.
Whoops.
Or genuinely extreme but clinically important events, like a critically low vital sign. Identifying them requires statistical methods like z-scores or the interquartile range, IQR, or more advanced anomaly detection algorithms.
And you can't just delete them all.
No. The decision to remove CAP or investigate an outlier always requires deep domain expertise. You can't just remove them without understanding if they're an error or a true rare event.
Makes sense.
And, of course, there's removing duplicates and resolving inconsistencies. Human error is a constant factor, leading to variations like Bill Jones versus William R. Jones, which should resolve to the same patient. Standardizing formats, like ensuring all phone numbers follow a specific pattern, is also crucial. Duplicate patient records or clinical events must be identified and merged to prevent skewing analyses.
Sounds like detective work again.
It really is. Finally, data quality assessment should be a formal process, not ad hoc. Researchers have developed frameworks to assess EMR data quality across multiple dimensions, including completeness, is expected data present, correctness, are values accurate, concordance, Do different data elements agree? Example, a diagnosis code matching a clinical note. And plausibility. Are values clinically believable? IG, a patient's AIDS isn't 200. It's a continuous effort.
Wow. Okay. Beyond just cleaning up typos or missing values, we face a deeper challenge: the language of medicine itself. How do you ensure shortness of breath is understood the same way everywhere, especially when different hospitals, different doctors, or even different systems might use slightly different terms or local codes for the exact same clinical concept?
That's the core challenge of terminology standardization, or what we sometimes call semantic harmonization. It's a huge hurdle.
Semantic harmonization. Sounds fancy.
It is, but it's crucial. Imagine a single clinical concept like hemoglobin A1C, a common blood test for diabetes. Across different labs or health systems, it might be documented with half a dozen different local names or internal codes.
Right, HbA1c, HgBA1c.
Exactly. If an AI model is trained on data from multiple institutions and those terms aren't matched correctly, the model will treat HbA1c, HbA1c, and glycated hemoglobin as three completely distinct, unrelated features.
Which means it misses the pattern.
It fragments the data, severely degrading the AI's ability to learn meaningful patterns and generalize across patient populations.
So how do you fix that? How do you standardize the language?
To solve this, the healthcare industry relies on a set of standard medical terminologies. SNUMED-CT, or Systematized Nomenclature of Medicine Clinical Terms, is one of the most comprehensive clinical terminologies globally.
Summoned. Okay.
It provides unique codes and concepts for a vast range of clinical information, including findings, symptoms, diagnoses, and procedures. Its hierarchical nature allows for concepts to be aggregated at different levels of granularity, from a very specific diagnosis up to a broad category.
So it organizes everything.
It tries to. LOINC, or Logical Observation Identifiers Names and Codes, is the global standard specifically for identifying laboratory tests and other clinical observations.
LOINC for labs.
Right. It provides a universal code for every conceivable test, measurement, and observation, ensuring that a serum potassium result from one hospital is electronically identical to one from another. This is crucial for comparing lab results across different providers.
Makes sense.
And then we have RxNorm, developed by the U.S. National Library of Medicine. It's a normalized naming system for clinical drugs, acting as a universal translator for medication data.
RX norm for drugs.
Yep. It links various drug names, including brand names, generic names, ingredients, and dose forms, to a single, unique identifier. This helps to unify medication data no matter how it's locally described.
So these are massive undertakings to implement, right? Mapping all your local terms to these huge standards.
They really are. The process of mapping an organization's internal local terminologies to these standards is a significant, complex undertaking. It often requires specialized third-party software or a dedicated team of clinical informaticists.
Clinical informaticists.
Yeah.
Another specialized role.
Exactly. People who understand both medicine and data to build and maintain these complex crosswalks. It's a foundational step that enables truly unified data analysis and AI model training across diverse data sets.
But even with standardized terminology, data from different hospitals might still be structured differently in their underlying databases, like we talked about with Epic versus others.
True.
So what does this all mean for conducting massive multi-site studies or building AI models that need to learn from data collected across an entire region or even globally? How do you harmonize the structure of the data itself?
This is exactly where a common data model, or CDM, becomes indispensable. And the OMAP CDM, Observational Medical Outcomes Partnership Common Data Model, has emerged as the leading open source standard for observational health data.
OMAP CDM. Okay.
Developed and maintained by the multi-stakeholder OHDSI, Observational Health Data Sciences and Informatics, collaborative, its core purpose is to transform data from diverse proprietary sources and formats into a single, common structure with a common standardized vocabulary.
So it maps everything to one standard structure.
Essentially, yes. It effectively converts the complex, proprietary, and highly normalized schema of a source EMR like Epic into a standardized, person-centric set of tables that are easy to understand and query. Key tables include person for demographics, visit occurrence for patient encounters, condition occurrence for diagnoses, drug exposure for medications, procedure occurrence for procedures, and measurement for lab results and vital signs.
Got it. Standard tables, standard names.
And each table uses the standard terminologies we just discussed, like SNOMED, LOINC, and ArcSnorm.
So it's essentially a universal translator, but for the entire database structure rather than just individual terms. What's the biggest payoff for an organization to make this upfront investment? Sounds like a lot of work.
Precisely. And the true power of FOMA extends far beyond just its data model. It's an entire analytical ecosystem. Transforming an institution's data into the OMOP CDM is a significant resource-intensive project, often taking years.
Years. Wow.
But this upfront investment is a truly strategic decision that unlocks access to a global suite of open-source analytical tools and, crucially, a massive research network. Once data is in the OMP format, an institution can use tools like ATLS to build complex patient cohorts with a graphical interface.
Okay.
They can download and run standardized analysis packages developed by the OHDSI community accelerating research. And perhaps most importantly, they can participate in federated network studies.
Federated studies, what are those?
In a federated study, the analysis code, not the patient data itself, is sent to each participating institution to be run locally on their OMP standardized data. Only the aggregated anonymous results are returned to a central coordinator.
Ah, so the data never leaves the hospital.
Exactly. This allows for massive international studies across millions of patients without ever sharing sensitive patient-level data, dramatically increasing statistical power and accelerating the pace of research from question to evidence.
That's huge for privacy and scale.
It's a game changer for large-scale AI development because it allows models to learn from truly vast, diverse data sets while still protecting individual privacy.
Okay. Before any of this data can be widely used for research or AI, there's a non-negotiable step: protecting patient privacy.
Hmm.
In the U.S., this means dealing with IPA, the Health Insurance Portability and Accountability Act. This is a huge concern for patients and institutions alike.
Indeed, it's paramount. The purpose of de-identification under IPA is to strip personal identifiers, known as protected health information or PHI, to enable its use for research and other secondary purposes.
Right. Remove the names, addresses, etc.
Exactly. Once properly de-identified, the information is no longer considered PHI and falls outside the scope of most of the privacy rules restrictions, enabling its use for research without individual patient consent. This is how large-scale studies are made possible.
So how do you actually do that? How do you de-identify data under HIPAA?
IPA provides two distinct methods for de-identification. First, there's the safe harbor method. This is a prescriptive, rule-based approach. It requires the explicit removal of 18 specific types of identifiers for the individual, their relatives, and their employers.
18 specific things. Like what?
These identifiers include names, all geographic subdivisions smaller than a state, with specific rules for 3-digit ZIK codes based on population density, all elements of dates except for the year.
Wait, all dates except the year, so no exact dates.
Correct. No precise dates of service, admission, or discharge are allowed under safe harbor. Also, telephone numbers, email addresses, medical record numbers, and full-face photos, among others.
Wow, and ages.
A critical rule is that all ages over 89 must be aggregated into a single category of 90 or older to prevent identifying very old individuals.
Okay. Safe harbor sounds simple, but losing all precise dates seems like it would severely limit what kind of AI models you could build.
Right. It's a massive trade-off for advanced AI. The safe harbor method, by removing all date elements except the year, makes it impossible to calculate precise time intervals, like the number of hours or days between a medication administration and a change in a lab value.
And that timing is often critical.
Absolutely. This temporal information is a critical feature for many advanced time-aware neural network models that try to predict future events. So, safe harbor significantly reduces the utility of the data for certain types of analysis.
So what's the alternative if you need those dates?
The second method is the expert determination method. This is a statistical principles-based approach. It requires a person with appropriate knowledge of and experience with generally accepted statistical and scientific principles.
An expert.
Yes, an expert, to determine that the risk is very small, that the information could be used alone or in combination with other reasonably available information to identify an individual. This expert must thoroughly document their methods and analysis.
So it's based on statistical risk, not just removing specific items.
Exactly. This approach is much more flexible and can allow for the retention of more granular data, such as full dates of service, more specific geographic information, or exact ages, if the expert can statistically justify that the re-identification risk remains very small.
Which sounds much better for building sophisticated AI.
It often is. This choice of de-identification method creates a fundamental tension between patient privacy and data utility, which has direct consequences for AI modeling. A research team planning to build a model that relies heavily on precise timelines must engage with their institution's data governance and compliance bodies early to advocate for using the expert determination method.
So you need to make the case for it.
You do. Furthermore, IPRPOA allows assigning unique non-identifying codes to de-identified data for internal relinking in longitudinal studies.
So you can still track a patient over time.
Yes, but the mechanism for doing so must be kept securely separate and cannot be disclosed with the de-identified data itself. This allows researchers to track a patient over time in a de-identified way without ever knowing who they are.
Okay, so now the data is cleaned, it's standardized, and crucially, it's privacy protected. It's finally in a high-quality structured format. But even then, it's not quite ready for AI to learn from it directly, is it?
Not usually, no.
This is where the art and science of feature engineering really come in. Think of the data scientist here as acting as a very smart guide for deep learning models, providing strong hints or domain-informed features that help the model learn more efficiently and accurately.
Precisely. Feature engineering is all about using your deep domain knowledge, in this case, clinical knowledge, to select, transform, and create variables that best represent the underlying patterns that a machine learning model needs to learn.
So you're helping the AI focus on what's important.
Exactly. While modern deep learning models can learn features automatically to some extent, for the complex, noisy, and sparse EMR data we've been describing, thoughtful feature engineering is still absolutely vital to guide the model, improve its performance, and make it more robust. It's like giving the model the right set of lenses to see the important details.
Okay, so how do you engineer features from that structured, time-based data, like vitals and labs?
Much of the structured data in an EMR, such as vital signs, lab results, or even medication timings, is temporal in nature, measurements taken over time, often at irregular intervals. Feature engineering for this focuses on capturing those dynamic and time-dependent properties.
Okay.
We use temporal aggregation and rolling windows to summarize data over clinically relevant time windows. For example, to predict a patient's risk of deterioration, we might calculate the mean heart rate, the min-max blood pressure, or the standard deviation of respiratory rate over the preceding 6, 12, and 24 hours.
So you're creating summary stats over time period.
Right. These transform long sequences of raw measurements into compact features that capture trends and variability.
So instead of just the raw number at one point, you're giving the model the context of that number over time.
Exactly. We also use lag features, which explicitly provide historical context by including past values of a variable as features for the current time step.
Lag features, like looking back.
Yes. So for predicting a patient's current glucose, you might include their glucose values from T1, 1 hour ago, T2 hours ago, and so on. This helps capture autoregressive patterns where past values influence current ones.
Makes sense. What about trends? Like, is something going up or down?
That's crucial. Trend features capture the rate of change or the slope over time. For instance, the change in white blood cell count over the last 48 hours is often far more informative for predicting infection than either measurement in isolation, as it indicates active deterioration or improvement.
Right. The direction matters.
Absolutely. For cyclical features like hour of day or day of week, simply encoding them as integers, 0.23 for hours, can mislead the model into thinking hour 23 is far from hour 0.
Because 23 is numerically far from 0, even though time wraps around.
Precisely. To preserve their cyclical nature, we transform them using sine and cosine functions, mapping them onto a circle. This way, the model understands that midnight is close to 11 p.m. and 1 a.m.
Clever. Mapping time to a circle.
And for high-frequency data like electrocardiograms, ECG, frequency domain features can be extracted using a Fourier transform to reveal underlying periodic patterns not always apparent in the raw time domain. These features can be powerful indicators of cardiac abnormalities.
Okay, that covers structured temporal data. Now, remember that vast sea of unstructured data, the clinical notes. You called it a narrative goldmine.
It really is.
Unlocking that information is absolutely critical for comprehensive AI in healthcare. But how do you convert doctors' free text, all their abbreviations and shorthand, into something a neural network can actually understand and learn from?
Unlocking that information requires a sophisticated two-step feature engineering process. First, information extraction, and second, text representation.
Okay, step 1, extraction.
For information extraction, we use natural language processing, or NLP, to turn that prose into structured, usable data. Named entity recognition, NER, is key here.
NER, finding the important words.
Exactly. It identifies and classifies specific entities within the text, such as diseases, symptoms, medications, dosages, anatomical sites, and medical procedures. State-of-the-art NER models, often based on transformer architectures we'll discuss shortly, like BioBERT, are specifically trained on large biomedical text corpora to achieve high accuracy in this specialized domain.
So it learns medical jargon, like SOB for shortness of breath.
Precisely. Or CVA for stroke. Once entities are identified, relation extraction determines the relationships between them. For example, it can identify that a specific drug was prescribed to treat a specific disease, or that a symptom is an adverse effect of a particular medication. This turns raw text into a knowledge graph, essentially.
That's amazing, turning a narrative into structured facts.
Uh,
But then how do you convert that structured text, or even the raw text, into numbers that a neural network can actually process?
Then comes text representation, converting the extracted information or the text itself into a numerical format that neural networks can process. Traditional methods like bag of words or TF-IDF, term frequency inverse document frequency, represent documents based on the frequency of words.
Yeah, counting words.
Right. While simple, these methods completely lose information about word order and, crucially, context. So, patient denies chest pain and patient has chest pain would be treated similarly if only looking at the words chest and pain.
Not good. Context is key.
Exactly. Modern NLP relies on dense embeddings, which are vector representations. Models like Word2Vec learn a vector for each word, where words with similar meanings have similar vector representations. Even more powerful are contextual embeddings from large transformer models like BERT.
BERT again.
Yes. These models can generate a single vector representation for an entire document or sentence that captures its deep contextual meaning, taking into account the complex interplay of all the words within it. This rich embedding vector can then be used as a feature input for a downstream prediction model. It's the difference between knowing a word and knowing what a word means in a specific sentence.
That sounds much more powerful. Okay, EMR data, once all this cleaning and processing is done, can become incredibly high dimensional. You mentioned thousands of tables earlier.
Right.
Imagine tens of thousands of diagnosis codes, hundreds of lab results, and thousands of concepts extracted from notes, all as separate features. This can really make it tough for models to learn, a problem often called the curse of dimensionality. How do we simplify this without losing important information?
That's a critical challenge, and it's where dimensionality reduction techniques come in. They aim to reduce the number of features or variables while preserving as much useful information as possible for the model.
Okay, fewer features, but keep the good stuff.
One very effective domain knowledge-driven approach is using clinical groupers. Instead of treating each of the thousands of specific ICD or CPT codes as a separate feature, they can be grouped into a smaller number of clinically meaningful categories.
It's like grouping different heart conditions together.
Exactly. For instance, the Charlson and Elixhauser comorbidity indices are well-established mappings that group ICD codes into 17 and 30 major comorbidity categories, respectively. This dramatically reduces dimensionality while creating more robust features that capture overall patient complexity or burden of disease.
Using clinical knowledge to group things logically.
Right. Then there are statistical techniques like principal component analysis, PCA. This transforms the data into a new coordinate system. The new axes, called principal components, are orthogonal and are ordered so that the first few components capture the largest possible variance in the data.
Finding the main trends in the data mathematically.
Kind of, yes. Think of it as finding the most important underlying trends in your data. By keeping only the first K principal components, you can significantly reduce dimensionality while retaining most of the information, kind of like compressing a large image into a smaller file size without losing too much detail.
And what about using neural networks themselves to help with this problem? Can they reduce dimensions too?
Absolutely. Finally, we have autoencoders, which are a type of unsupervised neural network. They are trained to reconstruct their own input.
Trained to copy the input. How does that help?
An autoencoder consists of an encoder, which maps the high-dimensional input to a lower-dimensional latent space representation, essentially a bottleneck, and a decoder, which reconstructs the original input from this compressed representation.
The bottleneck forces compression.
Exactly. After training, the encoder part of the network can be used as a powerful, nonlinear dimensionality reduction tool, transforming the input data into its learned compressed feature representation. For EMR data, which often has complex, nonlinear relationships between features, Autoencoders can be particularly useful in finding those efficient representations without explicit rules.
Okay. With our data meticulously prepared, features sculpted, and all those complexities handled, we finally arrive at the brain of the operation, the neural networks themselves.
Right, the models.
And for EMR data, we're not just using off-the-shelf models. The unique characteristics of healthcare data, like its irregular nature and time-dependent aspects, have driven the evolution of highly specialized deep learning architectures.
Indeed. The representation of a patient's health over time in an EMR is fundamentally a time series problem, a sequence of events. This makes sequence models a natural choice for modeling the patient journey.
Sequence models, like RNNs.
Exactly. For many years, recurrent neural networks, or RNNs, were the standard deep learning approach for sequential data. Unlike simple feed-forward networks, RNNs have loops, allowing them to maintain an internal state or memory of past information as they process a sequence step by step.
Okay, they have memory.
More advanced RNN variants like LSTMs, long short-term memory, and GRUs, gated recurrent units, were developed to overcome a critical problem called the vanishing gradient problem.
Vanishing gradient sounds complicated. Can you give us a quick, simple explanation of what that means and why LSTMs and GRUs are so important for fixing it?
Great question. Simply put, the vanishing gradient problem occurs in traditional RNNs when the model struggles to remember or learn from information that occurred many steps ago in a long sequence.
So they forget things easily.
Kind of. The signal from earlier steps becomes too weak by the time it reaches the end of the sequence. Imagine trying to follow a whisper across a very long room, it just fades out. LSTMs and GRUs fix this by incorporating gates, specialized components that learn to control the flow of information.
Gates. Like little traffic controllers for information.
Exactly. They selectively remember relevant details from many time steps in the past and intelligently forget irrelevant information. This makes them exceptionally well-suited for modeling long and complex patient histories where a diagnosis from years ago might still be highly relevant to a current condition.
Got it. Better memory for long sequences.
Right. However, while powerful, RNNs process data sequentially, which can be a computational bottleneck and still presents challenges in capturing extremely long-range dependencies efficiently. This is where the transformer architecture introduced in 2017 for machine translation offered a true paradigm shift.
Transformers. We hear about them everywhere now.
Its core innovation is the self-attention mechanism.
Self-attention. That sounds intriguing. How does a transformer self-attention mechanism fundamentally differ from how an RNN sees the data? And why was it such a game changer for EMR data specifically?
That's the crux of it. Instead of processing a sequence one element at a time, like an RNN, self-attention allows the transformer model to look at all other elements in the sequence simultaneously.
All at once, not one by one.
Right. It calculates attention scores that weigh the importance of every other element to the current one. Imagine you're reading a book, and when you get to a particular word, your brain immediately considers all other words in the sentence, and even surrounding sentences, to understand its full meaning. That's what self-attention does for the model.
So it sees the whole context instantly.
Exactly. This enables the model to capture complex, non-local dependencies far more effectively, and, critically, it allows for massive parallelization during training, making it highly efficient.
And why is that especially good for EMR data?
For EMR data, this is huge. A patient's EMR isn't a simple, dense, univariate time series. It's sparse, irregular, multivariate, and multimodal. The inherent limitations of RNNs in this highly complex setting spurred the development of new architectures.
So the field is adapting the models to the data.
Exactly. The field is now moving beyond simply applying off-the-shelf models to designing novel architectures that are fundamentally built to handle the specific structural properties of EMR data, such as asynchronicity between events, irregular time gaps, and multiple data types like lab results and clinical notes. This represents a critical step toward building more accurate and robust clinical prediction models.
Okay, if we connect this to the bigger picture, standard transformers are amazing, but EMR data has that dual structure. It changes over time, A and D, across different variables.
Right.
This has led to some truly innovative, specialized architectures that go beyond the basic transformer. Could you walk us through some of these, perhaps highlighting the one core problem each is trying to solve that was previously unaddressed?
You're right. Applying a standard transformer directly to EMR time series data is non-trivial because the data has relationships existing both across time and across different variables or event types. This has indeed led to the development of several innovative specialized architectures. One important bridge from RNNs, the TARNN, time-aware RNN,
Time-aware RNN.
explicitly addresses EMR challenges, particularly the irregular time intervals between observations. It incorporates irregular time intervals not just as a feature, but through a dedicated time embedding layer that modifies the input representation based on how long it's been since the last observation.
So it knows how much time has passed.
Precisely. Crucially, it uses a dual-level attention mechanism. One level of attention weighs the importance of different clinical visits over time, while a second level weighs the importance of individual features, like specific lab results within each visit.
Attention on visits. AND features within visits.
Clever. This not only improves predictive performance, but also provides valuable interpretability, showing why the model made a certain prediction by highlighting what it paid attention to.
Okay, so TARNN is smart about the time between visits and what's important in each visit. What's the next frontier these specialized transformers are tackling? Perhaps regarding asynchronous data where things happen at different times.
That leads us to pure transformer-based models. TransEHR is a self-supervised transformer model specifically designed to handle the asynchronous nature of real-world EMR data,
TransEHR, okay.
where continuous vital signs are recorded at different times than discrete events like lab tests or medication administrations. Its core innovation is using a unified triplet representation for every data point. It's not just a value, but a combination of variable, value, and time.
Variable value time, a triplet.
Right. This approach avoids the need to discretize the timeline into fixed bins, a process that can lose critical temporal information. TransEHR then uses the powerful self-attention mechanism to learn the complex temporal dependencies within these asynchronous sequences. It's like being able to read every word on a page, even if they were written at slightly different moments.
That makes sense. And what about when you have to consider both time and the type of event simultaneously, like a lab result versus a medication?
For that, there's DUA-T, Dual Event Time Transformer. This architecture explicitly attends over both dimensions of EMR data simultaneously, the time dimension and the event type dimension.
DUET, dual attention.
Right. It uses an innovative input aggregation method that transforms the sparse, irregular time series into a dense, fixed-length sequence. This not only makes the model aware of dual data structure, but also significantly reduces the computational complexity of self-attention, enabling the use of larger and deeper networks for more robust representation learning.
So it helps handle the complexity and sparsity.
Exactly. It essentially allows the model to efficiently understand what happened when across all the different kinds of medical events. And at the cutting edge, we have temporal graph transformers.
Temporal graph transformers. Sounds advanced.
It is. This approach models a patient's entire EHR as a temporal heterogeneous graph. In this structure, nodes can represent medical events like diagnoses or drugs and time-stamped visits. Edges capture relationships within a visit. For example, this drug was given for this diagnosis, and across time, linking visits chronologically.
So it models the connections between everything over time.
Very precisely. A temporal graph transformer can then operate on this complex graph, learning both the structured relationships between medical concepts and the temporal evolution of the patient's state over time, capturing a truly holistic view of the patient's journey.
Wow, okay. And then there's clinical text. This is where transformers have truly revolutionized the game, especially thanks to something called transfer learning.
Absolutely.
It's been a game changer for how we process and understand the vast amounts of narrative data in EMRs.
Absolutely. In the domain of clinical natural language processing, or NLP, transformers have had their most revolutionary impact, driven precisely by the power of transfer learning. The foundational model here is BERT.
BERT again. Bidirectional encoder representations from transformers.
That's the one. BERT was pre-trained by Google on a massive corpus of general text, like Wikipedia and books. Its key architectural innovation was the use of a masked language model objective, which allowed it to be trained to understand the context of a word based on both the words that come before it and the words that come after it, meaning it's bidirectional.
Seeing context both ways.
Right. This leads to a much deeper contextual understanding than previous models. The true breakthrough for healthcare came when researchers applied this transfer learning paradigm to the medical domain.
How do they do that?
Instead of training a model from scratch, they took the general-purpose BERT model and continued its pre-training on large, domain-specific text corpora. For instance, clinical BERT was further pre-trained on millions of de-identified clinical notes from public datasets, like MIMIC3.
So they gave Bird a medical education.
Essentially, yes. This process allowed the model to learn the unique vocabulary, syntax, abbreviations, and semantic relationships present specifically in clinical documentation. Similarly, PubMedBERT was pre-trained from scratch on text from PubMed abstracts and research papers, specializing it for the language of biomedical research literature.
So the model gets a general understanding of language first, then gets a specific medical education. How does that impact the feasibility and economics of actually building these AI models for healthcare?
That's where the game changer comes in. The power of this approach is that a research team or healthcare organization can now take one of these powerful pre-trained models and fine-tune it for a specific supervised task using a much smaller, custom-labeled dataset.
Fine-tuning, so you just tweak it for your specific problem.
Exactly. The model already has a deep understanding of clinical language. Fine-tuning simply adapts this knowledge to the specific task at hand. This has been successfully applied to a wide range of clinical NLP tasks. Things like automated medical coding, where the AI predicts ICD codes directly from a discharge summary. Clinical text classification, for example, classifying notes into subjective, objective assessment, and plan (SOAP) sections of a progress note, and even detailed information extraction, like identifying mentions of adverse drug events.
So it makes building these powerful NLP tools much easier.
Fundamentally, this transfer learning paradigm has fundamentally changed the economics and feasibility of high-performance clinical NLP. Previously, achieving state-of-the-art results required creating a massive, task-specific labeled data set, which was prohibitively expensive and time-consuming.
Right, labeling data is hard work.
Extremely. Now, the vast majority of the learning is accomplished in the unsupervised pre-training phase. This democratizes access to cutting-edge NLP, allowing smaller research groups and health systems to achieve remarkable results by fine-tuning these public pre-trained models on their local data.
So it shifts the cost from labeling to computing.
Largely, yes. Shifting the primary cost from labor-intensive data labeling to the computational resources required for fine-tuning. It means faster development and broader access to this powerful technology.
Okay, so we've mapped the technical odyssey, from raw data to cutting-edge neural networks. But building the model is only part of the story, isn't it?
Far from it.
The path from EMR data to a truly functional and impactful AI model is also laden with significant challenges that go beyond just the technical ones. This is truly a minefield we need to navigate responsibly.
You're right. The most sophisticated model can be rendered useless or even harmful if these non-technical considerations are ignored. Responsible AI development in healthcare requires a holistic approach that addresses crucial issues like fairness, interpretability, and real-world implementation from the very beginning.
Let's talk about fairness first. Algorithmic bias is a huge topic.
It is. One of the most critical challenges we face is the potential for algorithmic bias. AI models trained on historical EMR data are, in essence, mirrors of the past. They will inevitably learn and potentially amplify the biases inherent in the data and the healthcare systems that generated it.
So the AI isn't necessarily biased itself, it just learns the biases in the data.
Exactly. It's not about the AI being intentionally biased. It's about it faithfully reflecting patterns in the data it was fed.
So if the data itself contains biases, the AI is just going to learn them. Can you give us some examples of how these biases might show up in EMR data?
Absolutely. There are several common sources of bias in EMR data. Selection bias occurs because the patient population captured in an EMR is not a random sample of the general public. It's biased toward individuals who have access to and utilize healthcare services.
So it overrepresents people who go to the doctor often.
Right. This can lead to models that perform well on the sicker, more frequently seen population they were trained on, but might generalize poorly and overestimate risk when applied to the broader community or to underserved populations who don't access care as often.
Okay, what else?
Then there's information and measurement bias. The type and frequency of data collected for a patient are often correlated with their underlying health status or socioeconomic factors. For example, sicker patients tend to have more frequent visits and more lab tests, while healthier or less resourced patients have sparser data. A model might then learn to associate a lack of data with good health, which is a potentially dangerous, spurious correlation.
Wow. So missing data might be misinterpreted as good health.
It could be, yes. If a patient hasn't had many tests because they can't afford them, the model might incorrectly assume they're healthier.
That's scary.
And finally, we have systemic and societal bias. Healthcare systems have historical and ongoing inequities in access and quality of care based on factors like race, ethnicity, gender, and socioeconomic status. This is encoded directly in the data.
How so?
If a certain demographic group has historically received fewer diagnostic tests for a particular condition, an AI model trained on this data may learn to predict a lower risk for that group, effectively perpetuating a cycle of underdiagnosis and undertreatment. The model is simply reflecting the historical care patterns.
So how do you even begin to address something like that? It sounds like a problem that's much bigger than just the algorithm.
It absolutely is. Addressing bias is not a single technical step, but a continuous, multifaceted process that must be integrated throughout the AI model lifecycle.
A life cycle approach.
Yes. This isn't merely a technical problem to be solved with an algorithm, but a socio-technical one that requires significant human oversight and a fundamental commitment to equity. It begins with forming a diverse development team, including clinicians, data scientists, ethicists, and crucially, representatives from affected patient populations.
Involving the community.
Essential. To frame the research question in a way that anticipates and accounts for potential inequities. Strategies for mitigation include actively seeking out and including data from diverse populations during data sourcing, using data balancing techniques like SNOME or undersampling during pre-processing,
What?
employing fairness-aware learning algorithms during model training, rigorously disaggregating performance metrics across different demographic subgroups during evaluation, and implementing continuous monitoring of model performance and fairness on live data post-deployment.
So constant vigilance, basically.
And the human in the loop is crucial for high-stakes decisions and for auditing and updating the model as new data comes in.
Okay. Now, in the world of evidence-based medicine, a prediction without an explanation is clinically unactionable, right? Doctors need to know why.
Absolutely.
So what does this all mean for those complex black box AI models that are so powerful but often opaque? How do you get a doctor to trust a recommendation if they don't know why the AI made it?
That's a critical point. The black box nature of many complex deep learning models, where the reasoning behind a prediction is opaque, is a major barrier to their adoption and trust by clinicians. The demand for explainable AI, XAI, is not just an academic curiosity. It is a clinical, ethical, and legal necessity.
Explainable AI, XAI.
Right. Interpretability is essential for debugging models, building user trust, ensuring models are not learning from spurious or misleading correlations, and ultimately allowing clinicians to make truly informed decisions. If a model suggests a particular treatment, the physician needs to understand why to confidently follow that advice or override it.
So explainability is becoming as important as accuracy.
Increasingly, yes. The goal is no longer simply to maximize predictive accuracy. It is to maximize accuracy while also maximizing transparency. The explanation is becoming a first-class output of the model.
So how do you achieve that? How do you make AI explainable?
We have two main approaches to interpretability. Anti-hoc, or intrinsic interpretability, involves using models that are inherently simple and transparent, such as linear regression or decision trees.
Using simpler models from the start.
Right. You can see directly how they make decisions, almost like looking at a simple rulebook. The trade-off is that these models often lack the predictive power and ability to capture complex patterns that more advanced deep learning architectures offer, especially on highly complex EMR data.
So you might sacrifice accuracy for transparency.
Sometimes, yes. The other approach is post-hoc interpretability.
Explaining it after it's built.
Exactly. This involves applying techniques to explain the decisions of a pre-trained, complex black box model. As we discussed with transformers and TARNNs, their attention mechanisms can often be visualized.
Right, seeing what the model looked at.
Exactly. These visualizations can highlight which input features, which words in a clinical note, or which past clinical visits were most influential in generating a specific prediction, offering a crucial window into the model's reasoning process. It's like seeing the specific puzzle pieces the AI focused on.
Okay. What other post-hoc methods are there?
Another powerful set of techniques involves surrogate models, such as LIME and SHAPE. These are model agnostic, meaning they can be applied to any complex black box model.
LIME and SHAPE.
LIME, Local Interpretable Model Agnostic Explanations, works by creating a simple, local, interpretable model, like a simple linear model, that approximates the behavior of the complex black box model in the vicinity of a single prediction.
Can you give us a quick real-world analogy for how Lyme or SHAFE might work to explain a prediction?
Certainly. Imagine a complex AI model that predicts whether a patient is at high risk for a certain disease. Lyme would work by taking that specific patient's data, slightly tweaking it in many different ways, like changing one lab value or adding a symptom, and then observing how the complex AI's prediction changes.
Okay, perturbing the input.
Right. Based on those observations, Lyme builds a simple, local explanation for that specific prediction, telling you which features were most influential for that particular patient. It's like shaking a black box and seeing which parts rattle the most to understand what's inside, but just locally for that one case.
And SE.
SAP, Shapley Additive Explanations, based on game theory concepts, calculates the precise contribution of each feature to a prediction, providing a more robust and theoretically grounded explanation by considering all possible combinations of features.
So it assigns credit to each feature.
Essentially, yes. These techniques help us understand why a complex model arrived at a particular conclusion, which is absolutely vital for clinical acceptance and safety, and for debugging the model if it makes a strange prediction.
Okay. Beyond the data and the algorithms, getting AI to actually work in a clinical setting comes with its own set of very practical hurdles. It's not just about building the tech, it's about building it into a system with real people, real workflows, and significant organizational inertia. It sounds like there are many ways a brilliant AI model could fail in the real world.
You're absolutely right. The path to successful AI implementation in healthcare is paved with practical and organizational challenges that can derail even the most technically advanced solutions.
Like what? What are the big practical hurdles?
First, there are high implementation costs. The journey from raw EMR data to a deployed AI model is inherently expensive. It requires significant investment not just in the software and algorithms, but also in cloud computing resources, potentially hardware upgrades, complex data migration and storage solutions,
Right.
and extensive ongoing staff training to use and understand these new tools. It's rarely a one-time expense.
So it's a big commitment.
A very big commitment. Second, and critically, is dealing with staff resistance and workflow disruption. The history of healthcare technology is littered with examples of tools that failed because they did not integrate smoothly into clinical workflows.
Yeah, doctors and nurses are busy. They don't want more clicks.
Exactly. The clumsy rollout of many first-generation EMRs, which often increased documentation burden and led to widespread physician burnout, serves as a powerful cautionary tale. For an AI tool to be adopted, it must be designed with the end user, the physician, the nurse, the administrator at the center of the process.
User-centric design.
Absolutely. It must solve a real problem for them, be intuitive to use, and demonstrably improve, not hinder, their workflow. If it adds clicks or confusion, it will be resisted.
That makes total sense. What else?
Then there's the paramount importance of data governance and security. Protecting patient privacy cannot be overstated. AI systems must be built on a foundation of robust security, including end-to-end data encryption, strict access controls, and comprehensive audit trails to comply with regulations like IPA and GDPR.
Security has to be rock solid.
Non-negotiable. Any breach of patient data would severely undermine public trust and the viability of AI in healthcare for years to come.
And what about accountability? If an AI model makes a wrong recommendation and a patient is harmed, who takes responsibility? That seems like a huge issue.
That's a profoundly complex and largely unresolved legal and ethical question looming over healthcare AI, vendor reliability, and liability. Healthcare organizations often become dependent on their AI and EMR vendors for critical maintenance, support, and updates. A vendor's reliability and their long-term commitment are key risk factors.
Right.
Furthermore, if a model makes an error that leads to patient harm, who is liable? Is it the developer who built the model, the institution that deployed it, or the clinician who acted on its recommendation?
A very thorny question.
Extremely thorny. Establishing clear frameworks for accountability and liability is a critical prerequisite for widespread responsible adoption. Without clear answers, institutions will be hesitant to fully embrace these powerful tools.
Wow. Okay. You've just completed an odyssey with us. A true deep dive from a single data point in an EMR to a valuable feature powering predictive AI.
It's quite the journey.
We've navigated the labyrinthine EMR databases, built sophisticated data pipelines, standardized chaotic raw data, meticulously sculpted features, and explored cutting-edge neural networks designed specifically for the unique characteristics of healthcare data. This journey truly underscores the incredible technical complexity and the truly multidisciplinary nature of this entire endeavor.
It really does.
It's a testament to how many different fields have to come together to make this work: clinicians, data scientists, engineers, ethicists.
Exactly. The treasure within EMR data is indeed real, and its potential for transforming healthcare is immense. But as we've explored, unlocking it requires not just the right map and the right tools, but also the wisdom and foresight to navigate its complex terrain responsibly.
Wisdom and responsibility. Key takeaways.
Definitely. This raises an important question for all of us as we move forward. As AI becomes more and more integrated into clinical practice, how do you think we can best ensure that human wisdom, clinical intuition, and ethical considerations remain at the forefront, always guiding these powerful technologies for the benefit of every patient,